Hello, everyone, and welcome to the Geek Nighter podcast. I'm your host, Kaival Yapte, and I'm back with another episode on a database. So, today we are going to talk about an embeddable graph database called Kuzu, and I have with me Semih Salihoglu, who is an associate professor at the University of Waterloo and also CEO and co founder of KuzuDB. So, I'm really excited to dive deep into how KuzuDB works, some of its core features, and also compare it with other databases. So, Semi, thanks a lot for joining me today. And I'm really excited to have you here and talk about and learn more about KuzuDB.
Thanks very much. Thanks for having me.
Awesome. Let's start with a little bit of introduction about yourself, like what you do and how did you end up creating KuzuDB?
Yeah, so I am an associate professor at University of Waterloo, and I'm a core database researcher, if I'd like to label myself. I was trained, I get my PhD at a database lab, Stanford Info Lab, so it no longer exists. I was one of the last graduates from that lab. And back when I did my PhD, that was the big data era where people were building Spark MapReduce like systems. Spark was the star project back then, which kind of spinned off to Databricks. And I did my PhD on data analytics graph, but within the graph vertical. So there was a system called Pregel that was like MapReduce for graphs, and I wrote a PhD thesis on that system. And when I took my position at University of Waterloo, that's 2016, I did a survey on broadly on graph technologies, like how people are using them, what challenges they have. And part of the reason was in 2015 or 16, I forget, probably 2015, Mike Stormbreaker won an award, the Turing Award. And there was a book written by him, and I listened about the Turing lecture where he talked a lot about talking to users and getting feedback. I was inspired by that. And I was also a bit frustrated with my PhD thesis because it was like nobody was really using Pregel-like systems, and that was frustrating. So I didn't want to make the same mistake again. So I wanted to position myself in an area where there's enough movement, enough activity, but still wanted to stay close to my home expertise of graph analytics and graph databases. So in the user survey, this was published in 2017 at VLDB. 2017 it was published, but 2018 is I think when we actually got to present, and it won the best paper award to our surprise. And one of the things that we learned was that there's a lot of activity in graph databases. That's that's an area that Neo4j has created, basically. That's the system whose data model and query language are the most popular in this market. And they also had big scalability and performance problems. So that became very clear to me. So I studied that for my tenure case. My tenure case was basically, if we were to develop a new modern graph database management system, how would we do it? So I advised a PhD thesis, many master's theses in the space, studying the different architectural principles of how would we manage large-scale graph databases. And that was a project called GraphFlow, and that no longer exists. And by the time I submitted my tenure case, I had an idea about what the system should be like, and we can talk about that. But basically, the gap that we had seen was that the set of techniques that we knew about how to manage large graphs, and where I thought the current technology was, there was enough gap that I also said, okay, we can actually try to build a new system, and that's Kuzu, but with the goal of now being adopted by developers. We said if it goes well, maybe we can even spin off. And I'm talking about like end of 2020, basically, is when we started typing Kuzu. So I'm giving a long answer, but I hope this is fine. But one point that I want to make is that if you are a database graduate student, your dream is Postgres. Postgres is like the ultimate research project that's made great contribution to computer science broadly, and it's achieved much more than I'm sure what they originally imagined for. So there is this ambition that I think a lot of people idealize when we go to grad school in databases and study databases, that we want to work on a project like Postgres, where we write the system actually so that it can be used, and maybe there's an open source community. And there's been several examples of those. The last one is probably DuckDB, and I was quite close with them. And I was also liking how DuckDB kind of reminded us these embedded systems, how easy they are to use, and they had very good usability features that I was really liking. So then my idea was that I'd like to do a graph database engine with the principles from the GraphFlow system of how to manage large graphs, but borrow the usability features of DuckDB. So that's Kuzu started as with that goal, with that vision of let's try to build a DuckDB-like system, but highly optimized for graphs. So in a kind of a nutshell, that's the sort of the story of how Kuzu started. And now it's been about a little over 3 years that we've been working on this. We open sourced it a little over a year ago, so maybe a year and 3 months ago. And soon after we open sourced it, we got a few offers from investors that if we started a company, they'd invest. We took one of them. So there's also now a spin-off company around Kuzu. But we are still in the early ages where we're developing core technology. So it's not a product that we're selling. Our goal right now is to make the system more mature, more feature-rich, more robust, so that we get more and more adoption.
Awesome. Yeah. Yeah, that's great context and like why Kuzu was created and how kind of DuckDB inspired you. And SQLite inspired DuckDB and DuckDB inspired you. So that's a great thing. And as soon as I was looking at some of the documentation and the website, I looked at a highly scalable, embeddable graph database. And when I see embeddable, I compared it with DuckDB and SQLite. But this is very specific to graph type of data, like highly connected data, right? And when we say highly scalable, extremely fast, what does it mean for a graph database when we say highly scalable? For example, is it about the connections that a certain entity has, or it's just the amount of data or the concurrent queries we are talking about? So what does it mean in the context of graph database?
Good. So graph databases are primarily used for analytics-oriented applications. So that's historically too. I could also tell you the history of graph databases. It didn't start with Neo4j. It goes back to 1960s, even pre-relational world, there has been graph databases. But certainly after relational systems, the wave of graph databases that have come have primarily been for analytics-oriented systems. So the previous wave, for example, was RDF systems. That's also a graph-based model. And they're also used for highly analytics-oriented. When I say analytics, query-oriented, not really the primary maybe source of storage system where transactions get in, but it's usually a system to which data is replicated for some specialized application. RDF, we can talk about what RDF is being used, but for the property graph data model, which is the model proposed, implemented by Neo4j's, kind of that's their contribution to the field, one of their contributions to the field, and kind of picked up. And we also adopt a version of property graph model. So they're also used for analytics query-oriented applications. A couple of kind of classic examples are recommendation systems, fraud detection applications, maybe data integration applications. And when I talk about scalability in this context, being able to manage and store and query large data and with good performance. So that's a good way to think of this is maybe so Kuzu is a single node system. So any single node system obviously will have scalability limitations by the mere fact that you're limited to the hardware that you can put on a single node. But so a good way to think of this maybe sort of performant at scale, right? So maybe not as scalable as some distributed systems, which kind of is a core limitation of any single node systems, things like SQLite or DuckDB as well, but being able to manage more than the state of the art prior to Kuzu, and pushing the field in terms of query speed. So those are the two metrics that we are trying to optimize the system for.
Okay, very interesting. You also mentioned Postgres, which I consider, and you can correct me, but I consider it as a sort of gold standard when it comes to open source relational databases, and a lot can be built on top of Postgres. There's also some recommendation like use Postgres for everything. Whatever kind of data, Postgres will have some support for it. At some scale, I truly believe it can work really well, like in a cost efficient manner, in a good performance manner. But of course, there are some use cases which require some specialized techniques, like, for example, graph databases or graph type of data. Similarly, for when we talk about DuckDB, It's like high analytics, like let's say high scale analytics. And also, so when I talk about transactional versus analytic workload, like for transactionals, let's say I'm talking about a particular transaction, like an order for a customer or some other created an issue for a customer or a problem or a ticket or something like that. I'm talking about one entity. But when I talk about analytics, it's like a group of like millions of entities and some kind of aggregates on top of them.
That's right.
What does analytics mean in terms of a graph database? Is it the same analytic queries that I would run on different analytical database, or there's more to it?
So I felt like there was another question coming in about when should people switch to a graph database. If you want, I could come back to that question. But no, the final question ended up being what is a graph workload? So by its nature, no data is graph or relational. Data is data. It's the set of records that you have decided to keep in an enterprise for the needs of the enterprise. So data by itself is not in a particular logical form. So there are two popular logical forms. One is relations or tabular kind of modeling over your records, and the other is graph. It's always been like that. And that's very fundamental to computer science in general, too, that these are the two very natural data models, logical data models, with which you might want to model your data and run computations over it. Which data structure do I want to used when I'm modeling my data in your programs? And it's no coincidence that waves of database management system have usually fallen under one of these two. There's the relational systems and there's the graph-based systems. There has been more versions of this, but they're all, when we teach about graph databases, they're all under the sort of umbrella of graph databases. Tree-based systems, for property graphs are all versions of this. So what separates, so better question I think is what do graph databases try to optimize for? So that's a better way to define graph workloads. What have they observed that, there are these set of applications that ask these types of queries, and let's try to build systems that are optimized for that. That's usually the kind of the motivation for building new systems. Because after all, every system, every database is, if you take enough step high and look at all these systems, every system looks very similar in terms of the core functionalities that they give. The databases, this is how I teach databases or introduce databases in my courses. Databases are like cars. They all give the kind of a set of very core features, and you can build every application on top of every database. Usually it's a matter of which one is optimized better, which one is going to make it easier for you to build certain things, and which one is going to be faster, which one is going to allow you to store more data. Those types of sort of additional performance related or usability related features that kind of make the deal between which systems to choose. But the set of workloads graph databases try to optimize for are, so one typical thing is recursive queries. So queries of the form, maybe let's take a financial transaction application. Maybe you're a bank, you get a lot of financial transactions that you're modeling between accounts. And you are interested in queries of the sort, could this account A be transferring money to this account B? But the sort of the connections could be A, not direct, indirect, and B could be multiple kind of depth. And whenever you have queries of this sort, the natural sort of logical way you'd like to think about this is as a graph and a path in a graph. So you're really asking, is there a path between this node A and this other node B? And this is one reason people prefer a graph-based model, because paths are first-class notions in graph-based models. So you can, in Cypher, for example, which is the query language of Neo4j, also adopted by Kuzu, you can assign a variable to a path. You can draw a path pattern, and you can assign a variable to it, and now you can ask questions about the properties of the path. So whenever and that's usually a byproduct of asking recursive queries. And incidentally, the very first database in history was motivated by recursive queries like that. This is a system called IDS, just for, again, people who are interested in the history of data management broadly. The very first system in history is a system called IDS, which was based on a model called the network model. And the network is just another term for a graph. And it was really Well, actually, this is a bit inaccurate. But one of the first systems IBM built was IMS. I actually wanted to give an example of IMS. And an IMS system was built on a hierarchical model, again, a graph-based model. And it was based for essentially, it was trying to be very good at these recursive bill of materials types of questions. I'm building this big manufacturing engine. It's got multiple components which have subcomponents, and you're interested in how much steel do I need or how much iron do I need, which is a recursive kind of query. So that's one. Another one is that's typical is where you got many connections between the entities you're modeling in your records. Again, a financial transaction network could be good. So one account could be transferring a lot of money to a lot of other accounts, and they could be transferring money to a lot of other accounts. So this technically we could call a many-to-many relationships. If many-to-many relationships are prevalent, and if you're looking for patterns across these many-to-many relationships, again, thinking of these patterns as sort of graph forms is more natural to many people. So they try to optimize for essentially being fast on many-to-many queries. And then there's several of other kind of features that they try to optimize for. So one of them is being able to query the schema and the data at the same time. So stretching the example a bit more. So suppose you had a lot of types of transactions between your accounts, and you were looking for paths maybe, but you didn't want to specify exactly how the join could be. So normally in a relational system, if you have, say, maybe 3 types of transactions, maybe e-transfers, wires, and maybe direct transfers, direct deposits, you'd probably suppose you modeled these as 3 different tables. If you're looking for a path, meaning you're looking for a possible set of records that join, connecting account A to account B, you'd have to specify exactly which tables need to join in which order. But if you want more flexible querying where you say, I'm looking for a path, and I don't really care too much about the exact join path, which 3 tables connect in which way. That, or you have even maybe more constraints. I want paths, but I want the kind of the labels to have a particular string in them, maybe the word transfer in them. So you can't really ask these things in SQL, because in SQL you have to specifically write out what are your joins exactly, which tables are being joined. So if you wanted to say, I want to join 3 tables, and I want the final join to be across these tables with the word transfer in them, you can't really ask that in SQL. SQL doesn't have a syntax for that. So graph databases, or the languages built on graph databases, try to be flexible in terms of this flexible querying. So that's another one. And, I could continue for a few others, but maybe like these 3 are the first 3 that should come to people's mind about when do I need a graph database. Could we have queries that have a lot of cursive kind of connections that you're searching for in them? Are you looking for patterns across many-to-many joins, many-to-many relationships? And would you get benefit from being able to query the schema and the data at the same time, which usually you need if your data is very heterogeneous. If your data is very heterogeneous, it's very difficult to tabulate. And often for those kind of data sets, when you're querying for something, you may not know a priori exactly how to join things because the data is very complicated. So imagine cases where you have 2,000 or thousands of different types of labels or tables if you were to model them as relations, and you want more flexible query. So maybe I could highlight those 3 as the 3 kind of characteristics of graph databases. There's a few other, by the way, and this is a point where I could plug in for a blog post that I wrote initially when we first open sourced Kuzu about the set of features that I think graph databases should be good at. There's 2 more there, but these are, I think, the 3 core from the usability perspective.
Yeah, I will add that link to the blog in the YouTube description. And that's interesting, the 3 points that you mentioned, they are very interesting. But I want to take it to a little bit of extreme and look at it from a reverse angle. So if I believe that anything can be modeled as a graph problem, right? Like there are entities, there is relations, since the path is a first class citizen, I can model it in that way as well. So if I look at from the reverse angle and say that anything can be solved using a graph database. So what is the problem if I use graph database for all the existing scenarios as well, like where Postgres shines. So if I have to look at from the, let's say, downsides of using graph database for these traditional use cases like auto management system where I use Postgres, for example. So what
Yeah.
are the downsides?
So for Postgres, the answer is, I think, easier. So for Postgres it's a row-oriented system that's more competent in terms of transaction speed. So if you are, for example, looking for a system to which you'll be able to send thousands of transactions per second, you're building maybe an airline reservation ticketing system, and you need the system to be very competent at ingesting a lot of transactions, thousands of transactions per second. Graph databases are not a very good fit. Particularly, neither are, for example, analytics-oriented relational systems like DuckDB, for example.
Yeah.
Primarily because the storage and the way you're trying to ingest data is optimized so that it's faster at query, not really at writes. There's a fundamental assumption you make when you start developing these systems that, do I want to be optimized for queries, reads, in which case you're going to optimize your storage accordingly. You're probably going to pick a columnar system, for example. You're probably going to compress your data, which are all things that make reading fast, but it makes writing slower. There is this fundamental trade-off about what do you want to optimize for. And some systems obviously choose, depending on the workloads they target, they choose certain write optimizations versus read optimizations. So that's easy. It gets a bit harder if you try to compare a system like Kuzu and DuckDB, because like Kuzu, for example, looks at DuckDB in many of our core features. One obviously reason is, so there's a choice of what is a more natural data model for what I want to do. So if you're, for example, trying to generate dashboards about your sales, there isn't a particular benefit of modeling your data as a set of nodes and edges, and it might sometimes be a mismatch, actually. Graph-based modeling is a bit more object-oriented because you particularly say, here are my objects or nodes, and here are my relationships. That's particularly suitable for certain applications, maybe, but it's not really if you got logs or of these sort of lots of sales and you want to do tons of aggregations on certain things. But in the end, fundamentally, when you're building the system, I don't think there is particular principles in which a system like DuckDB optimizes for and Kuzu optimizes for, meaning that, forgetting about all the usability features and integrations you might want to do and the support you might want to give for certain applications. But at the core, sort of fundamental, there isn't something, I think, while Postgres and Kuzu would conflict on certain principles. For example, you would want maybe a row-oriented system for a system that wants to be very good at transactions versus a column-oriented system. So there's some certain areas where fundamentally, architecturally, you might differ between Postgres and Kuzu, but between DuckDB and Kuzu, it's more about, I think, the targets, usable, the applications that we're going to target, and the set of features that we're going to target, and the logical model we're going to expose. In fact, before Kuzu, with one of my co-founders who was a visiting PhD student of mine, Godong, we did propose to take a system like DuckDB and implement several of the core optimizations we are implementing in Kuzu on DuckDB, because they're not fundamental, they're doable. It's a matter of, do you want to do it for the type of applications you want to support? So optimizations like factorization or worst case optimal joins that are very critical and important for Kuzu because of the workloads we are assuming. For example, we are assuming many-to-many joins to being prevalent. They're not at any conflict with a system like DuckDB. So they could be over time integrated into these relational systems as well. And yeah, so there isn't that, but most of the engineering effort is going to be about how do you make your system more usable for the set of applications you're supporting. So in that case, there's a clear distinction between what the workload that DuckDB wants to optimize for and the workload that we want to optimize for in Kuzu. So Kuzu aims to be the go-to graph database for whenever somebody needs a graph data model and a graph query language. So that's where we are going for. So most of our efforts in terms of usability is try to make that a reality. Whereas I don't think that's even in the horizon for a system like DuckDB.
Okay, interesting. Let's get into some of the workings of KuzuDB. Like you mentioned, some of the optimizations that it does to support these high scale graph style queries. And that's a great point. Like when you say certain workloads are optimized for write heavy workloads, certain systems are optimized for write heavy workloads, as certain systems are optimized for query heavy workload. And we'll get into how Kuzu optimizes those workloads. Let's say I have to, taking the example of the financial domain that you mentioned, I have to ingest data into Kuzu, right? So what happens when I ingest the data? Do I use the Cipher query language to ingest as well? And what happens when the data reaches KuzuDB? How it is stored? What kind of optimizations are done at the right time?
Yeah. So during data ingest, so what we do is we do a set of standard things. So you want to do a bulk ingest from your Parquet files or CSV files from some raw files that are describing your nodes as a set of records and edges as a set of records. What we are going to do is for your node records, we are going to ingest the nodes into the properties of the nodes into columns. So you've got a columnar storage design in Kuzu, and you're going to create a hash index on the primary key of the node column. Suppose account IDs are the primary key. There's going to be a hash index that we built. It's a disk-based hash index that we built so that whenever you ask a question about a particular account, we can find that record very quickly. It's very standard things people build. Often, actually, they'll build tree-based systems. Hash-based systems are hash-based indices are easier to build, so that's why we started back in today. And so far, it's going fine. At some point, we'll have to implement a tree-based index as well. And then for your edge records, which is more distinctive of graph databases, is that we build a join index. So no relational system that I know does this. So when you essentially give a graph database a set of records saying these are edges between accounts and accounts, okay, so maybe these are my e-transfer edges. What pretty much every graph database does is that they build a join index. And you might hear the term like an adjacency list index to describe these, but in database literature, these are referred to as join indices. And basically, there is an implicit foreign key in your edge records. When you say an edge record is between from X to Y, those are two foreign keys to the accounts table or accounts nodes. Using those foreign keys, we'll build a join index, which will essentially, it's basically this index that for any account will give you the transfers that it has very quickly with a single or constant time lookup. And moreover, not using the primary keys, but the system level integer IDs. So when you ingest your nodes into Kuzu, every account in this example would get a numeric system level ID. These are essentially offsets in the pages that we store them, in the column that we store them. And the join index uses those integer IDs instead of maybe the primary keys, which might be strings. So which makes joins faster. This is an example of predefining a join, meaning that you tell the system a priori, these are edge records, but I'm going to use them to join accounts from accounts. So now Graph Database obviously use this to their advantage by building this join index, which makes certain joins faster. So that's one thing that is very distinctive of graph databases. We have a compressed sparse row, which is a very popular graph-based format to store graphs. We have a compressed sparse row-based join index. And we also store the properties on the edges in compressed sparse row indices. So that makes looking up a particular node and its connections very quick in the system. So those are, for example, queries where graph databases tend to be very fast at because they do all these optimizations a priori because they know these joins are going to happen a lot. Implicit in the modeling. When you say these are edges, the system assumes that, okay, a lot of joins are going to happen through these edges. And instead of, in a relational system, the system doesn't assume how the joins will happen, right? And you can join any two relations on arbitrary columns, which doesn't mean that in graph databases you can't do that, but graph databases are particularly optimized for the joins between the nodes that you have defined to the system through edges. That's the kind of steps that will happen, I think, at the storage levels and the indices that will be built.
Interesting. And that's the heavy lifting that happens on the right path because you are creating these indexes. And the key is to know what joins will happen, right? Otherwise, you cannot create those indexes. Like you mentioned, like on relational database, I just create a table and then I write query. And at the query time, I can define, oh, I want to write these joins and join these tables, right? And so write become lightweight in relational databases. But here, since you know that, okay, this is, something I have to create a join index on, the write becomes heavier.
Again, there's a spectrum within relational systems too. Like some systems are much lighter in terms of writes, whereas a system like, again, columnar systems like OLAP systems like DuckDB, they do a lot more optimizations during ingestion too. They, for example, a lot of them just do compression, which also takes time, which we also do. We are a columnar system, so we'll also compress your properties, the columnar properties that we store both for relations and the nodes. But that's right. So the join index, though, is very specific to graph databases. And actually, I don't think there's been ever a relational system that has built join indices, although it was proposed in 1980s that these could be built in academic work, but they never got adopted. But universally, every wave of graph databases that have ever come to the market have always assumed that they're going to build join indices.
Okay. And then it's pretty clear that since you're doing the heavy lifting on the right path, and you know that this is the join I'm going to use, that makes the queries faster, right? With this, I want to discuss what are the other optimizations at the query level, or queries are just quick. You have the indexes that were created on the right path and you get the data. Is it as simple, or there are more optimizations there?
There are several more optimizations that we do. Some of them are, again, none of these actually, this is interesting. I shouldn't say none of these. Many of these are just relational techniques. So this is one thing to understand too. Just the fact that graph databases expose a graph-based model and a graph-specific query language doesn't mean they're not relational. They are actually relational in the sense that all the queries that you write in graph databases, say in Cypher or Sparkle, which is a language of RDF, they all boil down and compile down to relational operators like joins, filters, scans, group bys, and aggregates. And this is something very fundamental because the only way we know of how to develop high-level query languages is to base them on relational algebra. So that's why, in that sense, when you look at a plan that, say, Kuzu generates, or Postgres generates, or DuckDB generates, or Neo4j generates, they all look quite similar. You'll all see similar sets of operators. So graph databases do not deviate from that common wisdom of how to develop high-level query languages and how to compile them to executable code. And that's why, actually, in fact, I say for all graph database languages, they are like SQL with some graph-specific syntax, but they are meant to be like SQL because that's really the only way we know of how to build query languages. There are differences. I know people discuss this a lot. I personally find it quite boring because, to me, they all look SQL. They should, and that's not a coincidence as well. So the point that I'm trying to make is that when we compile your high-level Cypher query into a query plan, that's gonna look very similar to your plans you'd get from Postgres. The kind of optimizations that will be done is more inside the operators that we'll have. So for example, we'll have join operators that use the join index, which, again, none of the relational systems would do because they don't build join indices. Another thing that we'll implement in Kuzu, and I think more graph databases certainly should adopt this, is we adopt a technique called factorization. And that's a technique for kind of compressing your intermediate relations that you generate in the query plans when the joins are many-to-many. So the big challenge of graphs and in general finding patterns across data sets that have many-to-many relationships is that the search kind of space over which you're looking for your pattern grows exponentially. So if I'm looking for maybe a 4-step path in a graph, or a 4-join, if you will, across some transfer tables, and on average, each account joins with 100 accounts, you're looking at 100 to the power of 4 search space. And out of those, maybe you have a pattern with some filters. That's what you're trying to essentially distill from. But your search space grows exponentially. So factorization is a technique It's a compression technique, but it's not a compression technique on storage. And it's one of my favorite kind of techniques academically when I was working on the graph flow system that I got to talk a lot about, work a lot on. And it is a technique not for storage, but it's a technique to compress the intermediate results that you generate as your joins explode. So a classic example could be, suppose all I want to do is I want to count the number of two paths transfers from account A to account B to another account C, from B to C, okay, two paths. And suppose I have a filter on the middle node that the B node is owned by KV, okay, owned by you. And suppose I'm essentially looking for, give me all two paths, give me all money transfers that KV might be facilitating. Okay, so where KV is the middle node, some money came to you and you've sent it to somebody else. Give me all of those and count me the number of paths, money kind of flows that KV might be facilitating. And suppose you have 1,000 incoming edges, 1,000 transfers that have been made to your account, and 1,000 transfers you made over some years over which we recorded your transfers. That's a search space of 1,000 times 1,000. Okay, so there's essentially a million the answer is a million. There's a million two paths that you might be facilitating. And if you did these joins, you would generate this intermediate table with a million rows, which would go into a counting operator that would count it. Factorization is the compression technique that observes, by just statically looking at the query, that in this query, if B is fixed, all the 1,000 incoming edges and 1,000 outgoing edges are independent, conditionally independent on the fact that once you fix B to KV, an account with KV, then all the incoming and outgoing edges, you're just going to take a Cartesian product there. So it instead represents the intermediate relation with essentially 1,000 sort of accounts or 1,000 edges times, meaning Cartesian product, with KV's account B times with 1,000 outgoing accounts. So it's compressed. So you never explode. You try to keep essentially the data as compressed as possible until you don't have to do this. So the counting operator actually gets something much more succinct than a million. It gets essentially a factorized tuple with 2,000 values in them, roughly. And it can do the counting much faster too, because it only needs to go through, look at the size of, like it's a single tuple with sort of three pieces. It looks at the size of the left vector, which is 1,000, right vector, and multiplies it. So that's a technique that's been introduced by Dan Olteanu, who is at University of Zurich now, and also part of Relational AI. And I fell in love with it basically because I could see how it could be used for graph workloads where you search for these many-to-many patterns. And so I worked a lot on that, and it's part of Kuzu. And there's a lot more work to do in that space, basically. I don't want to claim we know how to develop a factorized query processor, but Kuzu is the first serious attempt that I know. And so that's one optimization. And then there's a couple others. I may not go into them, but there's a new class of join algorithms called worst case optimal join algorithms, which again, Kuzu is one of the first systems to implement. But I think that's being recognized a bit more now. It's been 10 years since they were introduced. I did a lot of work on it and made sure it's part of the Kuzu apparatus so we can have operators that can do that. Yeah. So the query processor joins has been our focus, and we've got several optimizations in that. But importantly, Kuzu is the first, I think, serious implementation of a factorized engine that I'm aware of.
Awesome. Yeah, that's a very interesting technique, and I would love to go back and read more on that. So in a typical workload, right? Like I have a transactional system. Let's say I've been using Postgres, and then I say, you know what? I want to run these graph style queries where I have a lot of connected data from multiple sources. And you mentioned you want to ingest in bulk. Let's say you're reading your Parquet files or something like that, and where you already know the joins. But in mostly real world scenarios, I might need to add new type of queries. Let's say, I also want to join this data source now. So how do I do that in a graph model where the join index was actually created on the right path, but now there's a new type of join or new source that I want to join? And how does that impact when does it happen and how does that impact the storage?
Yeah, good question. In cases where you haven't predefined your join as a set of edges to the system, we fall back to regular hash join type of joins where we can't use the index
Okay.
and we have to do standard value-based joins. So that's the kind of the alternative predefined joins is value-based joins where you specify what your join is. You say, I got these set of records A from this table or node table, let's say, and I got this records B, maybe from an accounts and maybe some locations or whatever, right? Some other table. And you haven't defined any relationships between them, but you want to say that where A dot, maybe it has a property location is equal to location dot name. Right? That's a typical sort of join that you would do in SQL, in relational systems as well. We'll fall back to an operator. It's an equality operator, so we'll fall back to a hash join operator. Yeah, so there isn't something special that we do. But maybe you are even referring to a case where if you are going to do this within the system, you need to ingest it as a set of nodes, right? Without that, we don't yet have a capability to join with maybe a CSV, which we might be able to do it. I'm not sure, but we got very limited. Like DuckDB, for example, does that much better. I think in DuckDB, you could go to Postgres and even MySQL and even DuckDB tables and join things across, all based on values. Right? If we have features like that, which we want to do, where we want, for example, we don't have this yet, but we want you to be able to go to Postgres and say, here are my kind of some node records, and here are some relationship records, and here's maybe some native data in Kuzu, and you want to do some recursive joins across these things. Some of those, because of the lack of a join index, will be done without the join index based on values, and some of this will be done with using the join index. Yeah, so that's the fallback strategy we have for those cases.
Okay, interesting.
Yeah, but one thing I wanted to mention though, I forgot. So aside from factorization, worst case optimal joins, another thing that you will see special in graph databases, and I'll be brief on this, is you'll see specialized recursive join operators. This is also universal across graph databases, not something specific to Kuzu. Graph databases, because paths are first-class notions, in their query language, they support these syntax for a common, I should say, recursive join computation. So something like shortest path. That's a very common operator. So you can write in, for example, Kuzu or memgraph, which is another system that implements Cypher, something like I've got an account node A, and you can draw an arrow and you can put transfer. Okay, so I'm looking for some edges from an account A, some sequence of transfer edges, and you can put the word shortest and close the arrow with B, node B. So you're looking for a path between a node A and an account A and an account node B, and you're looking for actually the shortest path. So there's a specialized syntax. Because it's special, immediately we can compile that to a shortest path operator, which is a recursive join operator. So it's going to fall back to an operator that does maybe a Bellman-Ford, classic Bellman-Ford algorithm type of shortest path, or even we don't have it, but some systems have Dijkstra's algorithm, which I think is a bad idea for a database engine. But some systems I've seen that you can see a Dijkstra operator. So those are the type of things that you might see in a graph database. For us, we have this one kind of global operator called recursive join that does several versions of shortest paths or transitive closure type of computations, where we compile directly based on the syntax in the query to these specialized recursive join operators.
Interesting. Let's talk a bit about the updates of data, right? So data also gets updated. Like not all analytic databases supports updates at a very high scale because updates are expensive, specifically when you store in a columnar format, let's say in a compressed format. How are the updates done and what happens to the indexes then?
Good question. So we are rewriting our transaction manager, which is not really about exactly, it is partly about how updates happen. And with that sort of rewrite, we're also updating the way we're going to be ingesting updates. So you're right that in general, again, systems do tend to make a choice between how fast do I want to be for queries versus how fast do I want to be for writes. And you make this trade-off between where you want to land in terms of your write speed and read speed. And we are quite closer to read optimized system. So the way we do the ingest right now is that if you are, suppose you've done a bulk ingest of a large database, and now you have minor transactions coming in. So maybe 10 edges that you're going to add. So they'll go to this write store, which is the secondary write optimized store, which will ingest quickly. And it won't be part of the original read optimized storage. So we have essentially a write optimized store and a read optimized store. This may or may not be the state of the art, by the way, but it was one of the first ideas across columnar systems that was proposed. It was an idea proposed by this system called C-Store back in the day. C-Store is academically a well-known system, one of the first columnar systems from academia. And they had this write store idea. There's more advanced idea, but we chose not to implement them. But because of the more complexity, not because of a better reason, but this is a simpler idea. So we ingest sort of transactions into these small updates into a write optimized store. And then from time to time, we're going to merge it with the read store. So which slows down reads a bit, because if you accumulate a lot in the write store, because so you always have to check when you're reading a column, for example, of node properties to say, has there been an update to this chunk that I just read? And if so, you need to go and do some secondary scans and lookups in that write optimized store. Yeah, so that's why in general, read optimized systems, say a system like DuckDB or Kuzu, it's recommended that you do bulk inserts from time to time instead of doing lots of small inserts, because small inserts are going to be, usually there's going to be some other thing that's done in the system to ingest the data quickly, but it's going to have the effect that some reads are slower, reads getting slower. Or if you don't do that as a system, what you have to do is you have to keep merging immediately, but that means the write time is very slow because you have to reorganize certain things, maybe recompress certain things and whatnot. So it is slower. Yeah, so that's the rough solutions that we have.
Okay, interesting. Talking again on the right path. So since we are creating join indexes and hash indexes, and since depending on the type of the data I have, it can be highly connected data, and I may have a lot of joins. What is the optimization done, or what is the sort of protection done to not have this crazy write amplification and having this problem of really slow writes because of the nature of the data?
Yeah, good. So what Kuzu does is, so Kuzu has this CSR-based storage for your relationships, for your join index. So it's a CSR. Let me just maybe briefly summarize what a CSR is. CSR is basically, you can think of it as an adjacency list index, but it's packed, meaning that if you have maybe 10 adjacency lists, 10 accounts, and 10 of them have maybe in total 200 transfers, right? So on average, let's say each account has 20 transfers. So the way CSR works is that you have this one long, essentially, column in which you write the 200 edges. And then you have the secondary column of offsets of length only 20, pointing to different parts in this longer 10, I said 10 accounts. So a smaller offsets array of size 10 with 10 pointers to different parts of this longer 200 length array or column. And each thing essentially offset identifies the beginning of an adjacency list, meaning beginning of where the transfers of that account start from. And there's going to be the next 20 will be the accounts for that particular transfers for that particular account. So this has this packing into a column has this, obviously, as you say, it's a bad design for writes, because when writes come in, you need to do extra work to shift things or make the column larger, and it's obviously not scalable. So what Kuzu does is we leave gaps after each array. So essentially, instead of 200, we're going to leave 240, maybe with 20% gaps. And then after each 20, we're going to leave a gap of 4. But it's a technique called essentially packed memory array, basically. This is a disk-based storage, but think of the column as an array. We're going to leave gaps at certain parts so that the shifts are amortized. So you don't need to shift too much when you insert data, and it's easier to find. And then the data structure, the storage structure has a way of balancing the writes. So that we leave these gaps between. It's actually part of the code now. It's a recent change. We used to pack, and then we used to do chunks of the column over and over again. But recently, for the last month or so, there's gaps in between. So that makes ingestion easier. But you need to do some sort of optimization like this. If you keep things essentially indexed, in B-tree has implicitly optimizations like this, where you've got pages that can point to other pages, so it ensures that you can always find some space, and it makes to defend the protective system against these bad scenarios where you'll have to write this very large amount of data due to a simple insert, for example.
Yeah, interesting. Since we have already compared, and thanks for giving that kind of sort of mental model where people can think about when to use a relational database versus when to use a graph database. But how does it compare with other graph databases? What are the specific, or rather, specific optimizations or specific use cases that Kuzu really excels at? Let's say comparing it with Neo4j or some other popular graph databases.
So what we are going for is, so first of all, in terms of the core architectural principles, we have chosen a very specific architecture, which I think is the right architecture for a single node system. It's very different than Neo4j's, and you'll have to probably talk to their main architects to see why back in the day, at least, they're a much older system, obviously. They made certain architectural decisions, but it's very different than us. For example, we are a columnar system. Neo is a row-based system, and Neo is much faster at writes, or optimized more for writes than reads, but we've consciously chosen to be a system that is highly optimized for querying and precursor joins, many-to-many joins, and things like that, finding patterns across many-to-many joins. So we have a columnar system. We have a vectorized system, so meaning instead of passing a single tuple between operators, which is called a volcano style architecture, query processor architecture, which, as far as I know, Neo is, and maybe other systems are too. We are a vectorized system, which is the state of the art in terms of analytics read heavy kind of query evaluation. We've got a factorized engine. So all these are what I would consider state of the art of the field, and we are trying to implement that system. So one of the motivations for Kuzu was, as I was working on graph databases in my tenure case, was noticing the gap between where the set of optimizations that I would see in broadly adopted, at least across systems, are, and where this kind of the field knew about how to do certain things faster. So we're trying to implement all these additional optimizations. So that's one difference. The other difference is that we are an embedded system. So we are trying to be the easiest to use system to do these graph analytics pipelines. So if, for example, you got records that are in tabular in some relational system. So maybe suppose you exported them into Parquet or CSV, and you want to model these as a graph, and you want to build a pipeline, maybe a machine learning pipeline, in which you're going to do some graph neural network embedding of these nodes, and you want a system to which you want to ingest these records, quickly get graph modeling, do your transformations, cleaning, etc., and then pipe to maybe a graph machine learning software like PyTorch Geometric. We want to optimize for that type of workloads, be the easiest to use system. So there's certain aspects, usability features and integrations we are trying to do to make people to be the go-to system. But whenever you want, you've got records on your systems, other data systems that requires graph modeling. You want to be the easiest system to put that into and quickly build a pipeline. And embeddability is one aspect of this. It makes it really easy to build these pipelines. You can put it into a script very quickly, no server setup. And the set of integrations that we choose is another kind of way you can try to make this workloads easier. And the third difference that we have is that because we have this broader vision of being the go-to system for graphs, we are trying to have features that are also make it easier to ingest RDF data. So that's the second popular graph model in the market right now. And it's something that I have a very high opinion of, despite building a system that's core a property graph model. In my mind, the property graph model and relational model are very similar. They're both, property graph is a little extension of relational modeling where you explicitly say these tables are node tables and these tables are relationship tables. At least that's the version that we have. We don't allow certain features like nodes can have arbitrary labels. We don't have that. You need to have a schema. You need to say these are account nodes, and so we are in that sense very similar to a relational model. And RDF is the opposite. It's the right model, I think, for very heterogeneous data. But I think that the set of query processing and storage techniques that you can have to be good at RDF is not very far from the set of techniques you would have for a property graph model. So although we'll have certain limitations of querying RDF with a language like Cypher, I think we can be fast at it. So we're directly optimizing for both models. So we've got a feature called RDF graphs, which we recently launched, that can natively ingest RDF data into Kuzu. And there is a notion of an RDF graph in Kuzu now. So the model has extended a little bit. Many systems do this with additional libraries, and we try to do it more natively and make it easier for people to also move their RDF data to Kuzu.
Interesting. Yeah, as you mentioned already a couple of times, so ease of use and ease of integration seems to be like at the center of developing Kuzu. And that's when it will reach the state where you say the easiest to integrate database when it comes to graph modeling. If I have to just to give a thought on that, Neo4j seems to be more a general purpose graph database, whereas Kuzu's vision at least seems to be this very similar to DuckDB, where they want to, if you want to have analytics and you want a simple database, easy to use, easy to integrate, let's say for your machine learning models, or where you can directly integrate with where you have your data like pandas or something else, you can easily embed that database. So is it similar to, say, when we talk about Kuzu?
I do have that ambition. We don't have the set of features there yet. I mean, DuckDB is 4 or 5 years ahead of us, but I do look up to DuckDB in terms of those usability features. So like the ability to query directly off of CSV files and pandas and data frames was a very good feature, and kind of, to my best knowledge, was introduced by DuckDB. And we want to be similar, that you've got these, or the integrations that DuckDB does with Postgres and MySQL as it's writing are great usability features that makes it very easy to get a very good OLAP engine on top of your records without moving your data around. So that's a very good feature, I think. And we want to have a similar set of features where we want to, if you've got sort of your records in Postgres and you want to model those as, you got your account records and you got your transfer records, but you want to do recursive queries, and Postgres is not going to be very fast at that. So we want to have sort of features where you can say, not only Postgres won't be very good at that, writing that in SQL is not going to be very pleasant either, because recursion is an afterthought in SQL.
Yeah.
So we want to make it easy for people to essentially model it off Postgres, and maybe we'll have features where you directly get Cypher over these different sets of sources that you might have. And this idea of being a system, a gluing system across certain sort of data, to realize that for graphs is, I think, up there in terms of our ambitions. We want to be the glue system, the go-to system. That's what I mean when I say go-to system. Whenever you want graph modeling of your records, we want Kuzu to be the one that has lowered the barrier the most, so that it's easier to use Cypher on top of your records and also move data to Kuzu, but maybe sometimes directly query it off of these other sources. So I think that's a very good usability feature, and we wanna move towards there.
Interesting. I know you have already talked about what's coming up, what's your vision, and what you have been trying to release in the future. But still, if you have to list down, let's say, a couple of features that are coming up and that you're working on actively, what would be those features?
One is this new feature that we released, is the very first version. This RDF graphs is the ability to move RDF data directly off of their raw formats, like turtle format or NT format or N3 format. These are formats to store RDF data. RDF has a different data model where you express everything as a set of triples. subject, predicate, objects. It's a knowledge representation system, actually. Being able to map that to Kuzu directly. We just released the first version of it. It's not highly optimized, so we got to get better at it and also take feedback from the community and try to grow in that RDF community of graph technology users. Second is these connections that we want to start having to some relational systems to do direct querying of those records. And third is some of our things are actually not that optimized. And some people who use Kuzu will find maybe some of our querying very fast, but they're actually naive. They're not very fast. One thing, certain things we're very fast, but like recursive joins, for example, we've never optimized that. So we have a better understanding of how to do recursive joins. So we'll have to rewrite that. We're also quite naive in our optimizer. So we do have an optimizer, but we never spent enough time in generating very high quality plans. And so there's things missing at the core. So these are both the scalability and performance of Kuzu is not nearly where we know it can be. So the system is going to get a lot faster and more scalable and also more mature, I think, over time with sort of these several core features that we are going to be optimizing for. One is querying off of relational sources, and the other is RDF graphs.
Perfect. I wish you and your team very good luck to achieving all those optimizations and reach the state where, let's say, DuckDB is, because that's the inspiration. And I look forward to all the developments that you will be doing on KuzuDB. So, yeah, thanks a lot for coming to the show and sharing the insights and sharing your view on relational versus graph and comparing with other graph databases. And more importantly, sharing your vision with KuzuDB. So I'm sure it is going to be very helpful for our viewers. So thanks for joining me. And yeah, I really enjoyed the discussion.
Yeah, thanks so much. Thanks for having me again.
Awesome. Thank you.